Guys, we're looking at a second type of exponential model today, which is y equals kb to the x. Why is this different to type 1? This time the variable, which I've called x, is now the power, whereas previously the variable was in the base. Note my variables are y and x in this example, but in the examples you'll encounter, those variables could be any chosen letter. You've just got to read the question and work out for yourself which are the variables. If you feel confident with this type of question, I still advise you to, and you think you don't want to see any more of the video, I do advise you to look at the end of the video where it's got the interpreting of the models, because often questions do have a part to them, usually worth 2 marks, which says interpret this, i.e. what does K actually mean, what does B actually mean, and students often do badly on this type of question, so I've just covered that at the end of the video. Anyway, suppose y equals 2e to the x, and the graph of that function looks like that, which is obviously not linear, it's not a straight line. If we take logs of both sides, using the log rule and applying the log rule again with the power, we end up with that relationship, that log y equals log 2 plus x log e. And so suddenly our variable x, which was in the power, is now brought down out of the power. And if we replace log y with y and x with x in that relationship, we end up with that. And this is a linear relationship along the lines of y equals mx plus c. Okay, so that straight line relationship, log 2 is the y-intercept, that would be the plus c in the y equals mx plus c, and log e is the gradient of the line. So what we're saying is, if we've got a relationship where x is the exponential and we take logs, we can rearrange that and we can form a linear relationship, as you can see this straight line here, and we use that straight line to tell us something about our original exponential relationship. So here's an example, y equals kq to the x. Okay, there's no relationship, no straight line relationship between y and x, but there is between log y and x. So if we have this relationship where x is the power, then we take logs of both sides and replace log y with y and x with x, we end up with that linear relationship there. So again, that's the summary of the 3 bits. That's our original relationship. That's what we get when we take logs, and then when we do our substitution, this is our straight line relationship. And from that we can see that log k is the y-intercept on our straight line, and log q is the gradient. Okay, try an example. So in this example, we've got a mole population, and our exponential relationship is that the population is, we think, is of the form AB to the power of t, where t is time in months, so that's varying, so t is our variable, the population is varying, and a and b are constants, and that's what we're trying to find, a and b. Well, if p equals ab to the power of t, let's go through the process. Let's take logs of both sides and then bring the power down, and therefore we have a relationship between y and x of the form y equals log a plus x x log b. And that's a straight line graph. Log A is the y-intercept and log B is the gradient. Okay. So remember that that's the relationship of the straight line y equals log A plus x log B. And those were our substitutions in order to obtain that relationship. We let y equal log p and x equals t. So from our original table, which is here, our x value is just t. So we're going to keep these t values that were given to us. But we don't want the p values, we want log of p. Those will be our y values. So we're setting up a new table in order to draw this straight line graph. When t is 2, x stays at 2. And when p is 72, y equals the log of p, which is 1.85. When t is 3, x is still 3. And when p is 86, y is the log of 86, which is 1.93. So you go through the table, compiling your x value. Obviously, the x values are just the t values given to us, as you can see. And then our y values are the log of p values. And it's that second table we are going to use. And there it is at the top there. That's the table of values that we're going to plot. So there's our graph. We start plotting our values. And roughly it forms a straight line. It's not a precise straight line. This is measured data, and with it you're going to get inaccuracy, so it won't form an absolutely perfect straight line, but it's a pretty good straight line. And our job now is on those points to fit in a line of best fit. And it will look something like that. It might be a bit different, but that's a decent line of best fit. Now, looking back at what we did previously, log A is the y-intercept and log B is the gradient. So we want both the y-intercept and the gradient of this line. So first of all, to find the gradient, the change in those y values is 0.72. Sorry, can I just make a point up here? You might have thought, why didn't that red line come straight down from the blue point here? Why is it sort of in one? The reason is because this blue point doesn't fit exactly on this straight line. That straight line just goes through to there where my highlighter is, okay? And the blue, the very last top blue point is just off that line, okay? So the change in y, as you can see, is 0.72. The change in x is 8.8. And therefore the gradient of that line is 0.72 divided by 8.8, and that's 0.085. Now remembering that log b is the gradient, then log b equals 0.085, so b equals 10 to the power of 0.085, and that's 1.22. Log A is the y-intercept, and as you can see from the graph, the y-intercept there is about 1.68. So log to base 10 of A is 1.68, which means that A is 10 to the power of 1.68, and that's 47.9. Okay, so now we have found our values B and A, or best estimates for those values. And that gives us specifically now the relationship, okay, between the population and the number of months. Now, interpreting. Often you get asked to interpret the values of A and B, or whatever the constants are. Now, what you don't do is you do not write that log A is the y-intercept and log B is the gradient. That's not what it's asking. It's asking you to interpret what A and B are in the context of the question. So our question is about months and moles. So it should have something to do specifically with the question. Well, when t equals 0, given that we're measuring t, which is a number of months, when t equals 0, that's the very start of the study. And p will equal ab to the power of 0. b to the power of 0 is 1, so that just gives us p equals a. Therefore, a is the size of the population at the beginning of the study. So what we would write is a is the initial number of moles. Okay, so we're interpreting what A is in the context of the question, which is about moles. So how do we interpret B? Well, when t is 0, P equals A. When t equals 1, P equals A times B. When t equals 2, P equals AB squared. So as the number of months here increases, our population is being multiplied by B each time. So B is the proportionate monthly increase in the mole population because we're multiplying by a scale factor of B every month. So interpreting the question, I'm using the word monthly because our time is given to us in months, and it's just a proportionate increase, and it's in moles because we're talking about moles. Okay. So to recap for type 2, which is where we've got the variable in the power, take logs of both sides, use the first log rule, multiplication rule, use the power rule, and we end up with that relationship there. We let big Y equals log Y and big X equals X, and we end up with that relationship, which is linear. Log A is the y-intercept, log B is the gradient, and when we interpret our values A and B, A represents the initial value and B the proportionate change. Now often that power is time, t, so it's B would be the proportionate change per unit of time. And that unit of time depends on the units given to us. In our example, it was months, but it could be days or hours. Just depends on the question. Okay, folks, so for you, exercise 14H, which we'd started in the lesson previously, on page 331, those 4 questions there all have your variable in the power. Good luck with those, and as ever, if there's a problem, just drop me an email.